Oh, it's so nice, dude. I wish I should have started on campus. It's funny, most people start on campus and move off. I started off campus. Dude, no, that's so much better. I can charge $50 for missing a cleaning check, and having landlords that don't want to kill you is great, and just screw you for everything.
That's true. As far as the benefit side of it, it's
fantastic. And the thing is, I'm a senior now. I'm like, I can just be chill and not have to care, because it's not like I have. I don't really care anymore. 24, I'm good.
Which building are you in?
I'm actually, it's one of the upperclassmen buildings.
Is that the one next?
Yeah.
Okay, I live.
What did you like about it? I mean, it's chill. You have a lot of roommates, but even then, I was in a place
No, I have the same number. I don't know the setup.
Why not? Oh, really? Oh, mine does. This is the first apartment I've had a thermostat that works, but I was like, the other thing weird is my phone. All of my office was this is like, let's say like all my experience on off campus has been like call me 15 times. And tell them a month later, and some 20-year-old with no idea what you're doing. You're off this anything. So I did. It's right over here, Wendy's. Right off campus. It was really close.
Good afternoon, everyone. Welcome to class. Let's go ahead and get underway. I'd like to begin with prayer, and so I am looking for a volunteer. Please.
Heavenly Father, we're so grateful for this opportunity we have to be here in class and to be able to learn lessons, Lord, that we'll be able to understand the concepts and be able to be inspired as to the way that God's created things, and help us to be better students and to be more compassionate towards one another as well, especially during this chaotic time. Help us to find opportunities to serve. This is we pray in the name of Jesus Christ. Amen.
Amen. Thank you very much. The exam officially starts Thursday and runs through Wednesday of the following week. I am hopeful that we will finish all of the materials that will be on the exam by Wednesday, but we may spill over a little bit into Friday's lecture. I will be having some additional office hours or review sessions, however you want to consider them. I do have a study guide for preparing for the exam. So if we could get this around. Also, quiz 2 has been distributed last class, and here's a hard copy of that if you need. We're going to be talking extensively about hemoglobin over the next couple lectures, and so I have a handout with regards to that. So you can mobilize the TAs here to get those around. The handout describes in detail many features of hemoglobin, and I don't expect you to know all of the details on that handout. but it is a reference that you can use if you are trying to understand something that is discussed in class or presented on the slides or talked about in the book. So hopefully it's able to recapitulate those things that are critical. Those will be what are discussed in class. Those are presented on the slides or are in the book. Okay. Are there questions about any of that? Yes. What would your recommendation be? So the issue is, I'm happy to let it go till Monday. The issue is the study guide won't be available until Monday late. So if you're okay with that, I'm happy to have the quiz come in Monday by 5 p.m. Okay. All right. Any other questions or issues that you have, either sort of administrative in nature or content in nature? Okay. Let's then go ahead and move forward. I am going to use a number of PowerPoint slides. I will come back to the board in a few minutes and walk through some of these concepts, but I am going to now use some PowerPoint slides. Last class, we had talked about and derived something called the Hill equation. And that is shown at the top of this slide. So the term theta represents the fraction of protein with ligand present on it, bound to it, okay? So that's what theta represents. So it's the occupied fraction of protein, and it's equal to L, the ligand concentration, divided by L, the ligand concentration, plus the dissociation constant. I mentioned last time that the dissociation constant is actually a very valuable and important term or feature of any ligand-protein interaction. Very often, if you are interested in developing a drug, it is going to have an effect based on its ability to bind to and affect a protein. And so constantly people are calculating dissociation constants as they attempt to develop drugs. You don't want something that binds so tightly as to completely inactivate, let's say, an enzyme. Rather, you would like it to be able to reduce the activity of an enzyme rather than eliminate it. For example, I guess most people over the age of 65 or 70 are on a cholesterol lowering drug. These are termed statins, and they inhibit specifically an enzyme called HMG-CoA reductase. We'll actually see this in a later chapter. If you eliminate cholesterol from the body, you kill the person, okay? So even though high levels of cholesterol are problematic and can lead to clinical problems, you do not want to eliminate cholesterol from an individual. 80%, maybe as high as 85 or 90% of the cholesterol in our body, we synthesize ourselves. It's not from the diet. Now, if you have high cholesterol, you typically monitor your diet so that you don't you don't add to the problem. But most people with high cholesterol have high cholesterol because of genetics, not because of diet. Nevertheless, you don't want to make the matter worse. So here's a situation where you don't want an inhibitor, an HMGA-CoA reductase inhibitor, that is going to completely eliminate its activity. So you need to know its affinity. You need to know how much of the inhibitor to add to reduce the cholesterol by, let's say, 10 to 20%, not by 100%. Okay, so that is important. Now, we're going to consider another feature of ligand-protein interaction. There is something called cooperativity, and we're going to discuss that in just a minute. But to be able to determine if a protein-ligand interaction experiences cooperativity, one carries out what is called a Hill plot. And if you look at this complicated looking equation here, what has happened is this equation, the Hill equation, the theta equals L over L plus KD, has been converted in, it's the same, but it's been rearranged to be the equation for a line. So rather than working with something that is geometric in terms of its presentation, we're going to look at ways of plotting data so that we can linearize the data. If you notice, so, you know, this is like y equals mx plus b, but notice that this term n, the slope, has a special meaning. It is called the Hill coefficient, even though it's just the slope of this line. And if this term n, the Hill coefficient, is greater than 1, it indicates that there exists a condition called cooperativity. And what this means is that your binding affinity will increase as ligand concentration increases. If you have no cooperativity, you have constant binding affinity. But if you have a number, a positive number greater than 1, then you have positive cooperativity. And this is an indication that you have variable increasing ligand binding affinity as you add more ligand to a fixed amount of a protein. To be able to have this, you need to have a quaternary structure. You need to have a complex. This doesn't happen with a single, proteins that exist as single copies. But it requires now a complex of multiple proteins to be able to have cooperativity. Okay, this is the Hill plot for myoglobin and hemoglobin. And what you see here is there's a blue line running diagonally across this plot, and that is the plot of myoglobin. It has a slope that is equal to 1. What that says is that oxygen binds to every copy of myoglobin with the same binding affinity. On the other hand, you'll notice that for hemoglobin, you'll see that there actually are 3 regions. To begin with, down here in the sort of lower left-hand corner, down in this region, we have a slope of 1. This indicates to begin with that hemoglobin binds oxygen with 1 binding affinity. And you'll notice that up at the top, that as we get to higher levels of oxygen with the same number of hemoglobin tetramers, that you will also have another region where you have constant oxygen binding affinity. The difference between the two is that down here in the lower left-hand corner, we have lower binding affinity, and up at the top, right-hand corner, we have higher binding affinity. The thing that is interesting and important, as we will see for hemoglobin's function, is this region in here where we have a slope of somewhere around 2.8 to 3, which indicates that at some point, as we add more oxygen to the system, it causes the binding affinity to change, such that, let's say after you've added 1 or 2 copies of oxygen to a hemoglobin tetramer, the last 2 or 3 oxygens will bind with greater affinity. And in fact, right in this region where you have this, increased slope, it means that the binding affinity will actually increase quite rapidly as you add small amounts of oxygen. So keep this in mind, because we'll come back and we'll try to understand why that is so. Yes?
I noticed that the x-axis doesn't start at 0. How are we supposed to understand that? Like how we're supposed to, like, what is that? How do you have like less than 0 oxygen?
Yeah, well, that's a good question. I don't know. It's just what's in the book. So, in fact, both of those plots are that set up that way. Now, the log of that, I guess if you had a 0.5 something or other, maybe that gives you a negative number. Okay, so it's the function of the log that I think is making it look weird. Okay, so I don't think it means that you have a negative number doesn't mean you have no oxygen. It means you just have less than 1 mole of oxygen. Okay. Okay. All right. Let's take a minute now and talk about these 2 types of oxygen carrying proteins, myoglobin and hemoglobin. Myoglobin exists and functions as a single monomeric species, 1 copy of itself. It is found in skeletal muscle, and it serves as an oxygen storage protein. It allows these tissues that use oxygen, consume oxygen substantially, such as skeletal muscle, to have a local supply to be able to accommodate this. As shown in the Hill plot, myoglobin has a single oxygen binding affinity, and its binding affinity is stronger than the oxygen binding affinity of hemoglobin. And the reason for this is to be able to get oxygen to move into the skeletal muscle, to be able to store it at a higher concentration, the myoglobin needs to bind the oxygen more avidly than hemoglobin. Okay. Now, hemoglobin, functional hemoglobin, as found in red blood cells, has 4 copies of hemoglobin protein. In adults, this represents 2 copies of alpha hemoglobin and 2 copies of beta hemoglobin formed into this tetrameric species. Both of these proteins, well, actually, so we have alpha hemoglobin, beta hemoglobin, we have myoglobin. All 3 of these proteins fold spontaneously, and in doing so, produce a cleft or a pocket in their structure. So they are somewhat spherical otherwise, but they have this deep indentation, and that is going to be the site where we place a group, a molecule called a porphyrin ring. This porphyrin ring is the species. It's an organic macrocycle. We'll look at it in a minute, but it is the place where iron is bound. So the iron sits in the middle of the porphyrin ring, and the porphyrin ring is inserted into these different pockets. And we'll talk about that in just a minute. But interestingly, these three proteins actually have very little amino acid sequence homology. That is, they're only about 18% of all of the amino acids that are identical between these three different proteins. And even between hemoglobin alpha and hemoglobin beta, there's only about 50% homology. This is very unusual to have proteins that are so different in terms of their primary structure, their amino acid sequence, have similar function. But all three of these now fold into a structure that looks very, very similar. So all three of these, despite having markedly different amino acid sequences, produce in the final analysis structures that are very, very similar in shape, and consequently they do function very similarly. Okay, let's spend a minute now talking about the porphyrin ring. The actual official name for this is protoporphyrin IX. That's what it's called in the absence of the iron. With the iron present, we refer to this as a heme group. Okay, not hemoglobin. The hemoglobin represents the protein that will surround the heme group, but this represents this macrocycle, this organic macrocycle that contains the iron and is the actual binding site of oxygen. The protein does not bind oxygen. The heme group, in particular, the iron of the heme group binds oxygen. So you'll notice if you look at this, that it is we have this very tight and planar system. So notice there are all those double bonds. This is actually aromatic. That is, there's delocalization of electron density above and below the plane of the porphyrin ring. This probably has an important effect, having this pi system available, but what it is, we don't know. Okay. Additionally, you'll notice on one edge of the protoporphyrin IX, there are these two propionic acid groups. So 3 carbon extensions off of the ring system that end in carboxylates. These are negatively charged. And the consequence of that is that they will need to remain in contact with water. Okay. So as we begin to insert this ring system into the protein, we are going to be limited as to how deeply you can set the ring based on maintaining contact between these propionic acid side groups, and the aqueous environment. You'll notice that the iron is positioned in the center of the ring. We have a unique kind of bonding taking place. This is called transition metal bonding. It's sometimes called dative bonding. But what it represents is that there are pairs of electrons on those nitrogens, or some fraction of a pair of electrons on those nitrogens. And we have open d orbitals on the transition metal, on the iron. This is iron 2. It has to be iron 2, not iron 3. If it gets oxidized, we have problems. But you'll get overlap then of the d orbitals with these pairs of electrons on the nitrogens that form or are part of the porphyrin ring system, and they form these dative bonds. Now, there's something like a covalent bond in that you're sharing electrons, but they're a little unlike other covalent bonds in that you're not getting the contribution from two different nuclei to form the covalent bond. In this case, the nitrogens are donating and the iron is simply taking. And now, over on the right, you can see that we have a histidine imidazole ring. This is the only place where we have the hemoglobin protein bound to a feature of the heme group. Let me say it again. So this is the while we'll insert the heme group in the hemoglobin pocket, and it will fit very tightly. The only place where we have a strong chemical interaction between the protein and the heme group is this histidine. It's called the proximal or nearby histidine, and it's going to occupy a 5th binding site on the iron. The iron has octahedral symmetry. It has 6 coordination sites, 6 binding sites, and the 5th one is occupied now by the histidine, this proximal histidine, which is part of the hemoglobin protein. The 6th binding site, any guesses as to what its use is? Oxygen. Okay, so this is where we have the binding of oxygen. It's not to the protein per se. It's not to the porphyrin ring per se. It is bound to the iron of the heme group. And this is how oxygen then is carried. It's interesting that transition metal compounds, where you can think of any transition metal you want and surround it with any kind of organic ring system or ligand system, there are very, very, very few that can bind oxygen reversibly. Almost none. So it's the ability to bind oxygen reversibly is almost irreproducible in the laboratory. Despite years of effort, there are really very few transition metal complexes that can reversibly bind oxygen. Okay, let's stop here, take questions. Questions? Yes?
You said that with regards to reversibly binding oxygen, it's hard to do without iron, or just period for us to synthetically do that?
Synthetically do it in any way, shape, or form. Okay. It's just, yeah, the body's able to do it, and scientists have, but it has happened very infrequently, despite years and years, decades of research trying to create more oxygen binding proteins. Often in these kinds of situations, the metal ion will be oxidized, and the oxygen will be reduced either to superoxide or to hydrogen peroxide, and it will no longer be reversibly oxygen coming onto and off of that transition metal. So it's a feat that is hard to do. In fact, when I was at Yale, there was a gentleman there by the name of Bob Crabtree, who made his whole career out of synthesizing a couple of these compounds. So, yes?
So as you mentioned, the heat group said what attracts the heat group to the proteins?
Okay, good question. So it turns out, and this, you can see now we have myoglobin and hemoglobin beta. You'll notice that we're given this ribbon structure, and this is used to highlight secondary structure within the proteins. You can see that myoglobin and hemoglobin beta both have 8 alpha helices. Hemoglobin alpha only has 7. So, but it still has that pocket, that cleft, and the heme group, let's go back and look at it once more. Oops, I'm going the wrong way. This heme group is extremely hydrophobic, okay? And so is the pocket. And the heme group then spontaneously, as far as anyone knows, inserts itself into the pocket irreversibly. Those hydrophobic interactions, that hydrophobic bonding is sufficient that it doesn't really come out thereafter. I guess if you destroyed the protein, you might be able to liberate the hemoglobin, but otherwise the hemoglobin stays bound to the heme stays bound to the hemoglobin protein indefinitely. Again, let me point out, so this whole ring system here is very hydrophobic. It's planar, and we have these 2 carboxylates on this one edge, and as we insert the heme group into the pocket, those propionic acid side groups will need to be in contact with the aqueous environment. So it limits how deeply the heme group can be inserted into that pocket. Now this is important for a couple reasons, but one of them is that we need to align the proximal histidine with that iron. If we fail to do that, then I don't think we have the ability to bind oxygen, and we will not have the ability to change oxygen binding affinity, which we'll talk about in a minute. Okay. Let me point out an additional feature of the hemoglobin pocket. So again, this is myoglobin, but you can imagine this being hemoglobin beta or really hemoglobin alpha. Here we have this over on this F8. This is the F8 is this proximal histidine, and it binds to the iron. It represents the 5th ligand that is bound to the iron. Over here, though, on the E, this E7, 7 meaning it's the 7th amino acid in this E alpha helix, it is going to interact with the oxygen. And it's going to play a very critical role. It is going to reduce the reactivity of the oxygen. It's going to stabilize the oxygen. And in all likelihood, it prevents the oxygen from oxidizing the iron irreversibly, okay? So keep track of that. Okay. All right, let me now lose the screen here. Mess this up. My back. Okay. So let's talk about the organization of the hemoglobin. Okay, we've talked about the heme, the porphyrin ring, the heme group, and its insertion into hemoglobin. But let's talk about the formation of tetrameric hemoglobin. This is the biologically active form of hemoglobin. it is constructed, and they're not really boxes, but for simplicity's sake, I'm going to show this as our tetrameric hemoglobin, okay? And it's going to go as follows. We're going to have a alpha and a beta and an alpha and a beta. You'll notice that alpha doesn't interact with alpha and beta doesn't interact with beta. So this is the general overall assemblage of tetrameric hemoglobin. The interface between alpha 1 and beta 1, okay? So these actually hold together. Now, you think about it, we have these two random proteins that now recognize one another. That is, they have the right shape, the right topography on the surface of the protein to interdigitate with another copy of protein. Not only do they have the compatible and complementary shapes, they have binding interactions that hold them together. In fact, there are as many as 35 binding interactions between the alpha 2 beta 2 and the beta 1 alpha 1. These interactions are sufficiently strong that if you move alpha 1, it moves beta 1. Okay, so it's not like a hinge, a flexible hinge. This is like you've really glued them together, and so they will move largely in tandem. Along this axis, there are fewer. And this is absolutely critical for the correct functioning of hemoglobin. So 35 here, that's a substantial number of recognized complementary chemistries, positive charge versus negative charge, hydrogen bonding, hydrophobic versus hydrophobic. These are critical for this to stay together, but we need fewer here because it's going to turn out that these surfaces move across one another. We're going to have two broad conformations of the hemoglobin tetramer called T and R. After these move, they still have to hold together. So we have to move from one set of favorable binding interactions as this moves to another set of favorable binding interactions. How do these move? Well, so somewhere here we have our oxygen, our hemoglobin binding sites. I mean, the heme group fits in these pockets. When one copy of oxygen binds to this tetramer, it causes a change in the shape of the entire tetramer. Let me repeat that because it's important. One copy of oxygen binding to any one of these heme groups causes a very substantial change in the overall shape of the quaternary structure, the overall conformation of the tetramer. There is movement. So in some regions, there is as much as 6 angstroms movement as we bind oxygen, as we go from the T conformation to the R. So deoxyhemoglobin, where we have no oxygen present, is found in the T conformation. With one copy of oxygen, we move to this second structural conformation called R. Some features of this will move 6 angstroms, and there's rotation over the top of one another up to 15 degrees. Okay? So this is a pretty complicated series of changes that occur. Okay, any questions about this? Yes?
Is it 6 angstroms per diagnostic or just for the first one?
Well, So let me give a little bit of backstory for this. A long time ago, there was a man by the name of Max Perutz who crystallized deoxyhemoglobin and did X-ray diffraction studies and solved the structure of deoxyhemoglobin. When he took his deoxyhemoglobin crystals and exposed them to air, they shattered. And as he explored this, he found that there was, in fact, a second conformation called the R. Now, in terms of X-ray crystallographic studies, you can only observe two conformations, the T and R. But it's not that simple, as we will see. Okay, but so back to the question, a single copy of oxygen caused a significant change from T to R and movement of up to 6 angstroms. Let me go to a slide here. Okay, so this is going ahead a little bit. We'll try to come back. So this shows you the general structure of one copy of hemoglobin protein, well, one tetrameric hemoglobin. You can see that we have the gray and we have the blue. Those represent different hemoglobins. So we have beta 1 over here, we have alpha 1 down here. So this is the axis where there are 35 binding interfaces, where there are 35 binding interactions. Likewise over here. Now, as we go from T on the left to R on the right, you'll notice that indeed very little has changed, let's say right along here. Not much has changed between the left-hand T state and the right-hand R state. But if you look in the center here, let's say we look at this region right up here, it has now moved quite substantially relative to this gray piece over here. So if we think of this, this could be our 6 angstroms here. And there is some rotation of things over the top of one another, representing up to 15 degrees rotation. So some parts of the tetramer don't move much at all, but other pieces of this actually moves quite substantially. Yes?
Is there a rhyme or reason for the letters T and R?
Not really. So healing, the T stands for tense and the R stands for relaxed. So when I look at them, it looks like the species on the left is more open and relaxed than the one on the right, which is sort of more clumped up. But that's what he called them. So this is back to Perutz and his original. Okay, so we now are facing a situation. Oh, now as mentioned, as we bind one copy of oxygen to just one of these 4 hemoglobin proteins, we get this change in binding affinity. And so people have wondered, what is it that causes this change in oxygen binding affinity as you, first of all, move largely from the T to the R conformation, and then, as we saw with the Hill plot, there is a region where you have progressive increases in oxygen binding affinity as you add more ligand. How do you explain those more subtle changes in ligand binding affinity? So we're going to explore that. Let me go back though. I wanted to. Okay, let's spend our last few minutes with this slide because first of all, we want to consider how is it that oxygen binds? You know, so so you can see shown in red here is the porphyrin ring, this central ring. These groups around here, the valine, histidine, phenylalanine, histidine, these represent the protein. Not all of the protein, that would be too complicated to look at. But what they have done is they've isolated some of the side groups that seem to play an important role. As mentioned, the heme group, the porphyrin ring with the iron present, sits in a pocket. And it is bound there irreversibly. It is a hydrophobic pocket with two exceptions. You have the proximal histidine, this F8, and you have this distal histidine, E7. Those are the only two polar charged features in that pocket, and they have to interact with something else. They can't simply be by themselves for very long and be very happy because they are polar or charged. How does the oxygen make it to the iron? Okay. Well, the answer is we don't know exactly. We know that it is able to work its way through the protein, or maybe the protein heme interface on top of that ring. Remember, oxygen is nonpolar, and so it's able to do this. It's able to enter a hydrophobic environment, but it still has to work its way to the iron. It's able to do it in part because the protein is not rigid. It is not brittle. There is some motion, molecular motion, that is taking place. Not huge motions, but small vibrational, rotational motions that bring about something called breathing. And so the protein opens up slight channels or so forth that allows the oxygen to make its way in, and also to allow the oxygen to make its way out. It does no good to bind oxygen to the iron if you can't get it off. That is a recipe for disaster. So having the ring too deep would make it much less efficient to oxygenate hemoglobin and much less efficient to deliver oxygen to the tissues that it needs to supply. So the positioning of this heme group and the iron is absolutely critical. So the proximal and distal histidines help with that, but it is the propionic side groups that keep the position just right so that we have alignment, exact alignment of the proximal histidine with this iron. And this distal histidine is going to hydrogen bond with the oxygen and stabilize it, probably help bind it, but also make it less reactive so that it doesn't irreversibly oxidize the iron. These other groups here, the valine and phenylalanine, are meant to show that there's actually a small dome over the iron that allows the oxygen to sit on it. It is not crowded out. There's a bit of an opening just large enough in just the right angle to allow oxygen to bind at 120 degrees. So the tolerances, the dimensional tolerances on these on the protein, on the heme, on the iron, on the oxygen are phenomenal. If you were to move one of these groups an angstrom or two, it would likely cause the loss of the ability of the hemoglobin to bind and carry oxygen and deliver it. Okay, any questions about this? I think we'll make this the last slide for today. Anything from viewers? All right, let me share with you a story quickly. So when I was growing up, I didn't have a car for my own use. This is when I was in high school. I had a driver's license, but no car. But I had two friends that did have cars, and they were very generous. They would often take me to or from school, which was actually several miles away. One of my friends, John, had saved. He had worked summers, worked part-time jobs and so forth, saved his money, and he had bought a very old car. It was almost an antique at the time that he bought it, but nevertheless, it ran. And, you know, he bought the car, and it was remarkable. He took extremely good care of this car. He would vacuum it out. He actually washed and waxed the car. If he were going over a curb, he would go over very, very gently so that it didn't bump or drag on the road surface. My other friend, Rand, his father was a car salesman. And at some point in time, his father brought him home a brand new convertible. Very, very nice. Had these mufflers that kind of roared. People would turn and look, and it was a luxury car. It was a very, very nice car, and certainly far better than most of what the students drove to and from school. Now, Rand didn't abuse this car, but it was interesting. He didn't really clean it out. Papers would accumulate. Soda bottles and cans would accumulate. He didn't wash it. After a while, his father would get a little upset with him, and he would take the car into the dealership, and he would have some people there detail it, and they would come back, you know, cleaned, waxed, and so forth. And so it was kind of interesting to think about this, why my one friend with this extremely nice, very expensive car seemed to not put a lot of time and effort into its maintenance or upkeep. Whereas my other friend who bought this very old car, not very valuable, but nevertheless functional, spent a great deal of time servicing and maintaining his vehicle. Well, it's obvious that when we invest a lot, if we had to work a long time and spend a lot of effort to get something, we tend to value that more. On the other hand, if something comes very easily, often we don't realize the value of that thing. In life, even in the gospel, it is frequently the case that we ask for things that we are commanded to have, things that are desirable, things that are extraordinarily valuable, but we don't get them immediately. Sometimes we struggle for years to get something that we desire that we've been commanded to have. And I think very often it's just our Heavenly Father helping us understand just how precious a thing it is that we will get in the end. Anyway, something to think about. Thank you very much. And you're welcome.